Welcome to my channel Cogni Crafted Minds. In this video on cardiovascular health analysis, we'll walk you through the entire process of analyzing cardiovascular health data. We'll cover everything from importing necessary modules and loading the data information, data preprocessing, exploratory data analysis, target categorizing, normalization to building modeling and evaluating several machine learning models. Let's dive in. Introduction. This heart disease dataset, sourced from a reputable multi-specialty hospital in India, comprises a rich array of information encompassing 14 common features, making it a valuable resource for cardiovascular research. With a cohort of 1,000 subjects and 12 distinct features, this dataset serves as a pivotal tool for developing early-stage heart disease detection methods and constructing predictive machine learning models. Its diverse and comprehensive nature positions it as a significant asset in advancing research endeavors aimed at understanding and mitigating cardiovascular risks. Import modules. Let's start by importing the necessary libraries for our machine learning project. First, we import the Pandas library, which is essential for data manipulation and analysis. Next, we import NumPy, a fundamental package for numerical computations in Python. For visualization, we use Seaborn, a statistical data visualization library, and Matplotlib, PyPlot for plotting graphs. We also need to handle warnings, so we import the warnings library to filter out any unnecessary warnings. The term color library is used to print colored text in the console, which helps in distinguishing different outputs. For data preprocessing and model evaluation, we import several modules from scikit-learn. We use min-max scaler for feature scaling, and train_test_split for splitting our data into training and testing sets. Grid search CV helps in tuning hyperparameters, while cross_val_score and kfold are used for cross-validation. For classification tasks, we import random forest classifier, logistic regression, SVC, support vector classifier, decision tree classifier, K-neighbors classifier, and Gaussian NB for the naive Bayes classifier. We disable unnecessary warnings to keep our output clean by using the warnings, filter warnings function. Finally, we print a message indicating that all libraries have been successfully imported using the print function, with the message colored in blue for better visibility. Now, let's proceed with loading our dataset. We use Pandas to read the CSV file containing the cardiovascular disease dataset. The file is located at the specified path. We store the dataset in a data frame named df. To get a quick overview of our data, we use the head method to display the first 5 rows of the data frame. Additionally, we apply some styling to enhance the readability of the displayed data. We set the background color of the table to blue, the text color to white, and the border color to a shade of gray. This helps in distinguishing the data visually, making it more appealing and easier to interpret. Data information. Let's take a look at the first few rows of the dataset and some basic information to understand its structure and the type of data we're dealing with. Next, we will take a closer look at the structure of our dataset using the info function method. This method provides a concise summary of the data frame, including the class type, which in this case is Pandas, core, frame, data frame. The dataset contains 1,000 entries, indexed from 0 to 999, and consists of 14 columns. Let's go through each column. Patiented. This column contains unique patient identifiers and has 1,000 non-null integer values. Age. This column records the age of each patient, with all values being non-null integers. Gender. This column indicates the gender of each patient, with all values being non-null integers. Chest pan. This column captures the type of chest pain experienced, with 1,000 non-null integer values. Resting BP. This column contains the resting blood pressure values, all of which are non-null integers. Serum cholesterol. This column records the serum cholesterol levels, with 1,000 non-null integer values. Fasting blood sugar. This column indicates if fasting blood sugar is above a certain threshold, with non-null integer values. Resting R electro. This column contains the resting electrocardiographic results, all non-null integers. Max heart rate. This column records the maximum heart rate achieved, with 1,000 non-null integer values. Exercise angina. This column indicates if exercise-induced angina is present, all values being non-null integers. Old peak. this column contains the old peak values, with 1000 non-null float values. Slope, this column records the slope of the peak exercise ST segment, with non-null integer values. No of major vessels, this column indicates the number of major vessels colored by fluoroscopy, with non-null integer values. Target, this column contains the target variable, indicating the presence or absence of cardiovascular disease, all non-null integers. The dataset has one float column and 13 integer columns, with a total memory usage of 109.5 kilobytes. We'll delve into the descriptive statistics of our dataset using the describe function in Python. This function provides a summary of the key statistical metrics for each feature in the dataset, which helps in understanding the distribution and characteristics of the data. Descriptive Statistics Table 1. Features and Metrics. The table summarizes the descriptive statistics for various features in our dataset. Each row represents a different feature, and the columns provide statistical metrics for these features. 2. Key metrics. Count, the number of non-null entries for each feature. Mean, the average value of the feature. STD, the standard deviation, indicating how spread out the values are. Min, the minimum value in the dataset for that feature. 25%, first quartile, the value below which 25% of the data falls. 50%, median, the middle value of the data. 75%, third quartile, the value below which 75% of the data falls. Max, the maximum value in the dataset for that feature. 3. Understanding the metrics. Let's break down the statistics for a few key features. Age, mean, 49.24 years, indicating the average age of patients. STD, 17.86, showing a wide age range among patients. Min, max, the age ranges from 20 to 80 years. Quartiles, most patients are between 34 and 64 years old. Resting BP, resting blood pressure, mean, 151.75 millimeters of mercury, which is higher than normal blood pressure. STD, 29.97, indicating variability in blood pressure readings. Min, max, blood pressure ranges from 94 to 200 millimeters of mercury. Quartiles, 50% of patients have a resting blood pressure between 129 and 181 millimeters of mercury. Serum cholesterol, mean, 311.45 milligrams per deciliter, indicating the average cholesterol level. STD, 132.44, showing significant variability. Min, max, cholesterol levels range from 0 to 602 milligrams per deciliter. Quartiles, most patients have cholesterol levels between 236 and 404 milligrams per deciliter. Max heart rate, mean, 145.48 bpm, representing the average maximum heart rate achieved during exercise. Quartiles, 50% of patients have a maximum heart rate between 120 and 175 bpm. 4. Key insights. The average age of patients is around 49 years. Resting blood pressure and serum cholesterol levels show significant variability, indicating a diverse patient group. The maximum heart rate achieved during exercise varies widely, which is important for assessing cardiovascular health. Data preprocessing. Before we start our analysis, we need to preprocess our data. This involves handling missing values, encoding categorical variables, and more. To ensure our dataset is clean and ready for analysis, we need to check for any missing values. We use the isna.sum function method to count the number of missing values in each column. The output shows the following: patiented, 0 missing values; age, 0 missing values; gender, 0 missing values; chest pan, 0 missing values; resting BP, 0 missing values; serum cholesterol, 0 missing values; fasting blood sugar, 0 missing values; resting R electro, 0 missing values; max heart rate, 0 missing values; exercise anja, 0 missing values; old peak, 0 missing values; slope, 0 missing values; NUF major vessels, 0 missing values; target, 0 missing values. As we can see, our dataset is complete with no missing values in any of the columns. This is a great start as it means we don't need to perform any imputation or data cleaning for missing values. Having a clean dataset allows us to focus directly on our analysis and modeling steps. Next, let's take a look at the columns in our dataset. We use the df columns attribute to list all the column names in our data frame. The output reveals the following columns. Patiented, this column contains unique identifiers for each patient. Age, this column records the age of the patients. Gender, this column indicates the gender of the patients. Chest pain, this column describes the type of chest pain experienced by the patients. Resting BP, this column contains the resting blood pressure measurements. Serum cholesterol, this column records the serum cholesterol levels. Fasting blood sugar, this column indicates whether the fasting blood sugar level is above a certain threshold. Resting R electro, this column contains the resting electrocardiographic results. Max heart rate, this column records the maximum heart rate achieved by the patients. Exercise angina, this column indicates whether exercise-induced angina is present. Old peak, this column measures the old peak values. Slope, this column records the slope of the peak exercise ST segment. No of major vessels, this column indicates the number of major vessels colored by fluoroscopy. Target, this column is our target variable, indicating the presence or absence of cardiovascular disease. Knowing the column names helps us understand the structure of our data and guides us in our analysis and modeling steps. Now that we have a clear understanding of our dataset's structure, let's move forward with our analysis. Exploratory data analysis, EDA. Now, let's perform some exploratory data analysis to understand the distribution and relationships between variables. 1. What is the age range of patients in the dataset? To determine the age range of patients in our dataset, we'll find the minimum and maximum age values. Today, we're exploring the age range of patients in our dataset. By finding the minimum and maximum age values, we can determine the age span covered by our data. Answer. The age range of our patients is from 20 to 80 years. Understanding this range helps us grasp the demographics of the individuals included in our analysis, providing a foundation for further exploration of their health-related characteristics. 2. How many males and females are represented in the dataset? To answer this question, we need to analyze the gender column in our dataset. In this column, the value 1 represents female patients, and the value 0 represents male patients. Let's look at the distribution. Female. 1. Male. 0. The dataset contains only female patients. This is indicated by the gender column, where all values are 1, representing female patients, and there are number 0 values, which would represent male patients. Understanding the gender distribution is important as it informs us that our dataset is entirely composed of female patients. This insight is crucial for our analysis, especially when considering gender-specific health factors. Now, let's see the code in action. Next, let's determine the gender distribution in our dataset. We use the value _counts function method on the gender column to count the number of occurrences of each gender. Let's print the result. 1 to 765. 0 to 235. Explanation. In this dataset, the gender column uses 1 to represent female and 0 to represent male. So, we have 765 female patients and 235 male patients. Understanding the gender distribution helps us get a better sense of our dataset's demographics, which is crucial for any gender-specific analysis and insights. 3. What is the most common type of chest pain observed in the patients? To find the answer, we analyze the chest pain column in our dataset to determine the frequency of each type of chest pain. After counting the occurrences, we find that chest pain type 0 is the most common among the patients. Chest pain type 0 has the highest frequency in our dataset, indicating that it is the most commonly observed type of chest pain among the patients. Now, let's see the code in action. Let's explore the types and frequencies of chest pain reported by the patients. We use the value _counts function method on the chest pain column to count the occurrences of each type of chest pain. Here are the results. Type 0 to 420 occurrences. Type 2 to 312 occurrences. Type 1 to 224 occurrences. Type 3 44 occurrences. The chest pain column categorizes different types of chest pain experienced by the patients. Type 0 is the most frequently reported, followed by Type 2, Type 1, and finally Type 3 with the fewest occurrences. Understanding the distribution of chest pain types helps us gain insights into the symptoms experienced by the patients, which is vital for medical analysis and treatment planning. Now, let's visualize the relationship between chest pain types and maximum heart rates among the patients. We create a bar plot using Seaborn to show how maximum heart rates vary across different types of chest pain. The x-axis represents the types of chest pain, chest pan. The y-axis represents the maximum heart rate, max heart rate. Each bar in the plot corresponds to a different type of chest pain, showing the average maximum heart rate for that type. The colors in the plot are chosen from the Voridis palette to enhance visual distinction between the bars. Next, let's delve into the relationship between chest pain type and maximum heart rate. Title and axis. The plot is titled Maximum Heart Rate by Chest Pain Type. The x-axis represents different chest pain types, encoded as 0, 1, 2, and 3. The y-axis shows the maximum heart rate achieved by the patients. Bar colors and legend. Each bar represents the mean maximum heart rate for patients with a specific chest pain type. The colors help differentiate between the categories of chest pain. Observations. Type 0, dark blue, shows a slightly lower maximum heart rate compared to the other types. Type 1 and 2, teal and green, have higher mean maximum heart rates, indicating a possible relationship between these chest pain types and higher exercise capacity. Type 3, light green, shows a somewhat lower maximum heart rate than types 1 and 2 but higher than type 0. Understanding these relationships can help in diagnosing and managing patients with different chest pain types. 4. What is the average resting blood pressure among the patients? To find the answer, we calculate the average resting blood pressure from the resting BP column in our dataset. After computing the mean of the resting BP values, we find that the average resting blood pressure among the patients is 151.75 mm Hg. This average value provides us with a general understanding of the typical resting blood pressure levels observed in our dataset. It's calculated by taking the mean of all the resting blood pressure measurements recorded for the patients. Knowing the average resting blood pressure helps healthcare professionals and researchers gauge the cardiovascular health status of the patient population under study. Now, let's see the code in action. We're interested in understanding the average resting blood pressure among the patients in our dataset. We've calculated this by taking the mean of the values in the resting BP column. The result shows an average resting blood pressure of approximately 151.75 mm of mercury. This gives us a general overview of the typical resting blood pressure levels observed in our dataset. 5. How does serum cholesterol vary across different patients? To understand the variation in serum cholesterol levels among the patients, we visualize the distribution using a box plot. Now, let's see the code in action. We've created a box plot using Seaborn, which helps us understand the spread and central tendency of serum cholesterol levels. The x-axis represents different serum cholesterol values, serum cholesterol. The box plot shows the distribution of these values, including the median, line inside the box, quartiles, edges of the box, and any outliers, points outside the whiskers. The colors in the plot are chosen from the cool-warm palette to enhance visual clarity. The box plot shows the distribution of serum cholesterol levels in a sample of patients. The x-axis represents the serum cholesterol level, and the y-axis shows the count of patients. The box represents the interquartile range, IQR, which contains the middle 50% of the data. The line inside the box indicates the median serum cholesterol level. The whiskers extend to the minimum and maximum values within 1.5 times the IQR from the quartiles. Outliers, if any, would be plotted as individual points outside the whiskers. This plot helps visualize the spread and central tendency of serum cholesterol levels. It is useful for identifying the range of typical cholesterol levels and detecting any extreme values or outliers. 6. What percentage of patients have fasting blood sugar greater than 120 mg per deciliter? To find the answer, we calculate the percentage of patients with fasting blood sugar levels greater than 120 mg per deciliter. Now, let's see the code in action. We're interested in determining the percentage of patients with fasting blood sugar levels greater than 120 mg per deciliter. We calculate this percentage by first summing the instances where fasting blood sugar exceeds 120 mg per deciliter, then dividing this sum by the total number of patients in the dataset, and finally multiplying by 100 to convert it into a percentage. The result shows that approximately 29.60% of the patients have fasting blood sugar levels greater than 120 mg per deciliter. Understanding this percentage helps us assess the prevalence of elevated fasting blood sugar levels among the patient population, which is crucial for healthcare analysis and risk assessment. 7. What are the predominant resting electrocardiogram results in the dataset? To answer this question, we analyze the resting R electro column in our dataset to determine the counts of each type of resting electrocardiogram result. Now, let's see the code in action. We're examining the distribution of resting electrocardiogram results among the patients. We've counted the occurrences of each type of resting electrocardiogram result using the value underscore counts method on the resting R electro column. Here are the results. Normal, 0, 454 occurrences. Abnormality, 1, 344 occurrences. Unknown, 2, 202 occurrences. The values 0, 1, and 2 represent different categories of resting electrocardiogram results. Normal refers to a normal result, abnormality indicates an abnormal result, and unknown signifies results that are not categorized as normal or abnormal. Visualization. The scatter plot displays the relationship between age and maximum heart rate among individuals, with a distinction between those with heart disease and those without. Each point on the plot represents an individual, plotted with their age on the x-axis and their maximum heart rate on the y-axis. The points are color-coded to indicate whether the individual has heart disease, blue, or not, orange. The scatter plot is quite dense, showing a broad range of ages and maximum heart rates. Blue points indicate individuals with heart disease, while orange points indicate individuals without heart disease. There is no clear pattern or trend visible, suggesting that age and maximum heart rate are distributed widely across both groups. 8. What is the average maximum heart rate achieved by the patients? To find the answer, we calculate the average maximum heart rate achieved by taking the mean of the values in the max heart rate column. Now, let's see the code in action. We're interested in understanding the average maximum heart rate achieved by the patients in our dataset. We've calculated this by taking the mean of the values in the max heart rate column. The result shows an average maximum heart rate of approximately 145.48 beats per minute. 9. How many patients experienced exercise-induced angina? To find the answer, we count the number of patients who experienced exercise-induced angina. This information is extracted from the exercise angina column in our dataset. Now, let's see the code in action. We achieve this by summing the values in the exercise angina column, where each entry indicates whether a patient experienced angina during exercise. After performing the calculation, we find that 498 patients experienced exercise-induced angina. Understanding the prevalence of exercise-induced angina among the patients helps us assess the impact of exercise on their cardiovascular health and identify potential areas of concern. 10. What is the average old peak ST depression induced by exercise relative to rest among the patients? To find the answer, we calculate the average old peak value by taking the mean of the values in the old peak column. Now, let's see the code in action. We calculate this by taking the mean of the values in the old peak column. The result shows an average old peak of approximately 2.71. Understanding this average provides us with insights into the typical ST depression levels observed among the patients during exercise, which is crucial for evaluating their cardiovascular health. 11. How is the slope of the peak exercise ST segment distributed in the dataset? To understand the distribution of the slope of the peak exercise ST segment, we visualize the data using a count plot. This plot shows the frequency of each slope type in the slope column, helping us see how common each slope type is among the patients. Now, let's see the code in action. We've created a count plot using Seaborn to show the frequency of each slope type in the slope column. The x-axis represents the different slope types. The y-axis represents the count or frequency of each slope type. The colors are chosen from the Voridis palette to enhance visual clarity. The title of the plot is Distribution of Slope of Peak Exercise ST Segment, which helps us understand the prevalence of each slope type among the patient population. Here, we're looking at the distribution of the slope of the peak exercise ST segment, which is a crucial feature in assessing heart health. The x-axis represents the slope categories, ranging from 0 to 3. The y-axis shows the count of individuals in each category. We observe that Category 2 has the highest count, followed closely by Category 1. Category 0 has the lowest count. This distribution helps us understand how common each slope category is among the individuals in our dataset, providing insights into the prevalence of different types of ST segment slopes during peak exercise. 12. What is the range of the number of major vessels in the patients? To find the answer, we determine the range of the number of major vessels by finding the minimum and maximum values in the No of major vessels column. Now, let's see the code in action. We've calculated this by finding the minimum and maximum values in the No of major vessels column. The result shows that the number of major vessels ranges from 0 to 3. Understanding this range provides us with insights into the variation in the number of major vessels among the patient population, which is important for assessing the extent of coronary artery involvement. 13. What percentage of patients in the dataset have heart disease? Target equals 1. To find the answer, we calculate the percentage of patients with heart disease by dividing the number of patients with a target value of 1 by the total number of patients in the dataset. Now, let's see the code in action. We calculate this by dividing the number of patients with heart disease by the total number of patients in the dataset, then multiplying by 100 to get the percentage. The result shows that 58.00% of the patients have heart disease. Visualization. Now, let's see the code in action. We've created a histogram using Seaborn to display how age is distributed among the patients, with separate colors for each gender. The x-axis represents the age of the patients. The y-axis represents the count or frequency of patients in each age group. Different colors represent different genders. Muted colors are used for better visual clarity. We set the multiple parameter to stack the bars for each gender within each age group, and we used 15 bins to divide the age range into intervals. The title of the plot is Age Distribution by Gender, and the legend helps us differentiate between female and male patients. Let's examine the age distribution by gender. In this bar plot, the x-axis represents different age groups, and the y-axis shows the count of individuals within each age group. The bars are stacked to show the distribution between males and females. We can see that the distribution is fairly even across most age groups, with a slight variation. Both males and females are represented in each age group, with some age groups having a higher count of females and others having more males. This visualization helps us understand the demographic spread of our dataset, showing the age and gender distribution clearly. 14. Can you identify the patient with the highest age in the dataset? To identify the patient with the highest age, we first find the maximum age value in the dataset. Then, we extract additional details such as patient ID, gender, chest pain type, and target, indicating heart disease presence. Patient ID: 1,160,678. Age: 80. Gender: female. Chest pain type: 1. Target: 1. Heart disease. The patient with the highest age, which is 80 years old, is identified by finding the maximum value in the age column. This patient is female, reported chest pain type 1, and has been diagnosed with heart disease based on a target value of 1. 15. Who is the patient with the lowest resting blood pressure? To identify the patient with the lowest resting blood pressure, we first find the minimum value in the resting BP column. Then, we extract additional details such as patient ID, age, gender, chest pain type, and target, indicating heart disease presence. Patient ID: 119,250. Age: 40. Gender: female. Chest pain type: 0. Target: 0. No heart disease. The patient with the lowest resting blood pressure is identified by finding the minimum value in the resting BP column. This patient is a 40-year-old female, reported no chest pain, and does not have heart disease based on a target value of 0. This information provides insights into the characteristics of the patient with the lowest resting blood pressure in the dataset, highlighting various health-related attributes. 16. What is the correlation between age and maximum heart rate? To determine the correlation between age and maximum heart rate, we calculate the correlation coefficient. Correlation between age and maximum heart rate: -0.04. We're exploring the correlation between age and maximum heart rate in the dataset. The correlation coefficient is a statistical measure that quantifies the strength and direction of the relationship between two variables. The correlation coefficient of -0.04 indicates a very weak negative correlation between age and maximum heart rate. This means that as age increases, there's a slight tendency for maximum heart rate to decrease slightly, though the relationship is not strong. 17. Is there a relationship between chest pain type and the presence of heart disease? To explore the relationship between chest pain type and the presence of heart disease, we visualize the distribution using a count plot. Now, let's see the code in action. Using a count plot, we're visualizing how heart disease presence, target, varies across different types of chest pain. The x-axis represents the types of chest pain reported. The y-axis shows the count of patients. Each bar is divided into segments representing the number of patients with and without heart disease, denoted by different colors. The legend indicates no and yes for the absence and presence of heart disease, respectively. The plot compares the presence of heart disease across different chest pain types. The x-axis categorizes the types of chest pain, 0, 1, 2, 3, while the y-axis shows the count of patients. The red bars represent patients without heart disease, and the blue bars represent patients with heart disease. Chest pain types. 0. Typical angina. 1. Atypical angina. 2. Non-anginal pain. 3. Asymptomatic. Most patients with typical angina, type 0, do not have heart disease. A significant number of patients with non-anginal pain, type 2, have heart disease. Patients with atypical angina, type 1, and asymptomatic chest pain, type 3, also show a higher presence of heart disease compared to those with typical angina. To compare serum cholesterol levels between patients with and without heart disease, we'll visualize the difference using a box plot. Now, let's see the code in action. We're examining how serum cholesterol levels differ between patients with and without heart disease. Using a box plot, we visualize the distribution of serum cholesterol levels categorized by the presence or absence of heart disease. The x-axis represents the presence of heart disease, with 0 indicating no heart disease and 1 indicating heart disease. The y-axis shows the distribution of serum cholesterol levels. Each box plot provides a summary of the data distribution, including the median, quartiles, and any outliers. The box plot compares serum cholesterol levels between patients with heart disease and those without. The x-axis categorizes the patients into two groups: no heart disease and heart disease presence, while the y-axis shows the serum cholesterol levels. Each box plot shows the distribution of serum cholesterol levels for the respective group. The median cholesterol level is indicated by the line inside each box. The IQR is represented by the height of the box, showing the middle 50% of the data. Whiskers extend to the minimum and maximum values within 1.5 times the IQR, with potential outliers shown as individual points. This plot allows for a visual comparison of serum cholesterol levels between patients with and without heart disease. It can help identify any significant differences in cholesterol levels between the two groups, which might indicate a potential association between cholesterol and heart disease. To understand the distribution of old peak values among patients with heart disease, we'll visualize it using a histogram with kernel density estimation. Now, let's see the code in action. We visualize how old peak values are distributed specifically among patients with heart disease. The x-axis represents the old peak values, which indicate the ST depression induced by exercise relative to rest. The y-axis shows the count of patients. The plot includes a kernel density estimation curve, shown in coral, to provide a smooth estimate of the distribution. Distribution of old peak in patients with heart disease. The plot illustrates the distribution of old peak values among patients with heart disease. Old peak represents ST depression induced by exercise relative to rest. The x-axis shows the old peak values, while the y-axis displays the count of patients. The bars in the histogram provide a visual representation of how frequently each old peak value occurs. Additionally, a line smoothly connects the tops of the bars, highlighting the trend within the data. Interpretation. Old peak values range from 0 to 6. Most patients have old peak values between 0 and 4. There is a notable peak around the old peak value of 3, indicating a higher concentration of patients in this range. This plot helps in understanding how ST depression varies among patients with heart disease, which can be crucial for diagnosing and evaluating the severity of their condition. 20. How many patients have all three major vessels showing defects? Number of patients with defects in all three major vessels, 116. The count of patients with defects in all three major vessels is obtained from the No of major vessels column. Max heart rate by gender and heart disease presence. the relationship between gender, heart disease presence, and maximum heart rate. In this bar plot, we will explore how these factors interact. Title and axis. The plot is titled, Max Heart Rate by Gender and Heart Disease Presence. The x-axis represents gender, where 0 is typically male and 1 is female. The y-axis shows the maximum heart rate achieved by the patients. Bar colors and legend. The bars are color-coded based on the presence of heart disease. The color legend to the right indicates, dark blue represents patients without heart disease. Teal represents patients with heart disease. Observations. For both males, gender 0, and females, gender 1, the maximum heart rate is slightly lower in patients with heart disease compared to those without it. The difference is visually small, suggesting that while heart disease might affect the maximum heart rate, other factors could also play significant roles. By examining this plot, we gain insights into how gender and the presence of heart disease might influence the maximum heart rate of patients. Target categorizing. To balance the target variable, we might need to categorize or bin some variables. Let's see how we can categorize age into groups. Let's walk through to identify the unique target classes in our dataset. Inspecting target classes. First, we need to inspect the unique values present in the target column of our dataset. The value 1 represents the presence of heart disease. The value 0 represents the absence of heart disease. By identifying these unique target classes, we gain a better understanding of the binary classification problem at hand. This is a crucial step before we proceed with further data analysis and model training. Let's walk through the steps to replace the numerical target classes with descriptive labels in our dataset. Replacing target classes. We replace the numerical values in the target column with descriptive labels. This makes the data more understandable. Here, 0 is replaced with absence of heart disease, and 1 is replaced with presence of heart disease. Inspecting the first few rows. After the replacement, let's take a look at the first few rows of the data frame to confirm the changes. df head function. This command will display the first 5 rows of the data frame, allowing us to verify that the target column now contains the descriptive labels. By replacing numerical values with descriptive labels, we enhance the readability of the dataset. This is especially useful for presentations and reports, making it easier to understand the meaning of the target variable. Let's now proceed to view the first few rows of our modified dataset. Normalization. Normalization helps in bringing all features to a similar scale. This is especially important for algorithms like k-nearest neighbors. Let's go through the scaling our features using min-max scaling, creating features x and target y. We start by separating our data frame into features x_disease and the target variable y. x_disease now contains all columns except the target column. Y holds the target variable values. Min-max scaling. Next, we apply min-max scaling to normalize our features to a specified range, typically between 0 and 1. Here, min-max scaler scales each feature independently by compressing the range to the specified feature_range, creating scaled data frame x. We then create a new data frame x with the scaled features, maintaining the column names from x_disease. X now contains scaled values of the original features. Descriptive statistics. Let's generate descriptive statistics for the scaled features to understand their distribution. This command provides statistical summaries such as mean, standard deviation, min, max, and quartiles for each feature after scaling. The background_gradient method applies a color gradient to visually highlight different statistical values. Min-max scaling transforms the features to a uniform scale, making it easier for machine learning algorithms to process without bias due to differing scales among features. Now, let's review the descriptive statistics of our scaled features. The table provides a summary of the statistical properties for different features in a dataset. Each row represents a feature or variable, and each column provides a different statistic for that feature. Here's a breakdown of the columns. Count, number of non-missing, non-nan values. Mean, average value, STD. Standard deviation, which measures the amount of variation or dispersion of the values. Min, minimum value, 25%, first quartile, value below which 25% of the data falls. 50%, median, middle value of the data. 75%, third quartile, value below which 75% of the data falls. Max, Maximum value. Interpretation. Patiented. Each patient ID is unique, as indicated by the count being 1000 and the values ranging from 0 to 1. Age. The average age is around 48.7 years with a standard deviation of 0.297. The ages are evenly distributed between 0 and 1. Gender. The average value is 0.765, suggesting a higher proportion of one gender. Chest pain. The average chest pain index is 0.327, with values spread across 0 to 1. Resting BP. The average resting blood pressure is 0.545, indicating variability in blood pressure levels. Serum cholesterol. The average serum cholesterol level is 0.517, with a range from 0 to 1. Fasting blood sugar. The average fasting blood sugar is 0.296, with a standard deviation indicating significant variability. Resting electro. The average resting electrocardiographic result is 0.374, with a range from 0 to 1. Max heart rate. The average maximum heart rate is 0.569, indicating variability in heart rate levels. Exercise angina. The average exercise-induced angina index is 0.498, with values spread across 0 to 1. Old peak. The average old peak, ST depression induced by exercise, is 0.437, with a range from 0 to 1. Slope. The average slope of the peak exercise ST segment is 0.513, indicating variability. No of major vessels. The average number of major vessels colored by fluoroscopy is 0.407, indicating variability in the number of major vessels. This table is useful for quickly understanding the central tendency, dispersion, and range of each feature in the dataset. It helps identify potential data issues, such as missing values or extreme outliers, and provides insights into the overall distribution of the data. Let's walk through the steps involved in modeling and evaluating our classification results using Python. Modeling and evaluation, initialization and functions. We start by defining functions to visualize the performance of our classification models. Confusion matrix function. This function plots a confusion matrix to show the performance of our model in terms of true positive, true negative, false positive, and false negative predictions. Classification report function. This function generates a detailed classification report showing metrics such as precision, recall, and F1 score. These functions utilize Matplotlib and Seaborn for visualizing the confusion matrix and classification report. Confusion matrix. It provides a snapshot of the model's performance in terms of correctly and incorrectly predicted instances for each class. Classification report. It offers detailed metrics such as precision, recall, and F1 score, providing a more comprehensive evaluation of our model's performance. These functions are crucial for evaluating the effectiveness of classification models, helping us understand how well the models classify instances of heart disease presence and absence. Modeling. Now, let's build some machine learning models. We'll split our data into training and testing sets first. We use an 80-20 split for training and testing, respectively. Random forest classifier. Next, let's optimize our random forest classifier using grid search CV. This will help us find the best hyperparameters for our model. Now, let's see the code in action. First, we define a dictionary of parameters to test in the algorithm. This dictionary specifies the values we want to test for the number of estimators, the criterion for measuring the quality of a split, and the number of features to consider for the best split. Next, we create an instance of random forest classifier and use grid search CV to perform an exhaustive search over the specified parameter values. We'll use 20-fold cross-validation to ensure robust results. This code initializes the random forest classifier and grid search CV with our parameter grid. It then fits the model to the training data. Finally, we print the best hyperparameters and the corresponding accuracy score. The best hyperparameters for our random forest classifier are criterion, entropy, max features, log 2 feet, number of estimators, 500, and the best accuracy score achieved is 97.74%. Optimizing our model in this way ensures we get the best performance possible by fine-tuning the hyperparameters. After finding the best hyperparameters for our random forest classifier, let's train the model using these optimal parameters. We initialize the model with the best parameters obtained from grid search CV. This code creates a random forest classifier with the best hyperparameters and fits it to our training data. Next, we use the trained model to make predictions on the test data. This code generates predictions for the test data. Finally, we evaluate the model's performance by calculating its accuracy score on the test set. The random forest classifier achieves an impressive accuracy score of 98%. Optimizing and evaluating our model in this way ensures it performs at its best on unseen data, providing reliable predictions. Let's take a closer look at the distribution of our test dataset. This step is crucial for understanding the balance between different classes in our target variable. We check the count of each class in the test set. This command gives us the following counts: presence of heart disease, 132. Absence of heart disease, 118. In our test dataset, we have 132 instances where heart disease is present and 118 instances where it is absent. This relatively balanced distribution helps ensure our model's evaluation metrics are reliable and meaningful. We'll be looking at how our random forest model performed in predicting heart disease. Let's go through the results together. Confusion matrix. Starting with the confusion matrix, we can see how well our model did by comparing actual labels with predicted labels. True positive, bottom right 131. Here, 131 cases were correctly predicted as presence of heart disease. True negative, top left 114. 114 cases were correctly identified as absence of heart disease. False positive, bottom left 1. Only one case was incorrectly identified as presence of heart disease when it was actually absent. False negative, top right 4. There were 4 cases where the model failed to detect presence of heart disease when it was actually present. Classification report. Next, let's look at the classification report, which provides more detailed metrics. Precision. Precision for presence of heart disease is 0.97, and for absence of heart disease, it's 0.99. This indicates that our model is highly precise. Recall. Recall for presence of heart disease is 0.99, and for absence of heart disease, it's 0.97. This shows that our model is excellent at identifying actual positive cases. F1 score. The F1 score, which balances precision and recall, is 0.98 for both presence of heart disease and absence of heart disease. Accuracy. Overall, our model has an accuracy of 0.98, meaning it correctly predicts 98% of the cases. Conclusion. So, the random forest model is performing exceptionally well, with high precision, recall, and accuracy, making it a reliable model for predicting heart disease. Next, we move on to fine-tuning our logistic regression model using hyperparameter optimization. This process allows us to find the best set of parameters for our model to achieve optimal performance. Now, let's see the code in action. First, we define a dictionary of parameters to test. These parameters include different regularization strengths, C, class weights to handle class imbalance, and various solvers for optimization. We then initialize our logistic regression model. Using grid search CV with a cross-validation of 10 folds, we fit the model on the training data. After training, we print the best set of hyperparameters and the corresponding accuracy. The best hyperparameters found are C, 10, class_weight, balanced, solver, LBFGS. These parameters resulted in an accuracy of 0.96 during cross-validation. Fine-tuning our model in this way ensures that we are using the optimal configuration to achieve the best performance on our dataset. Now that we have determined the best hyperparameters for our logistic regression model, we proceed to train the model with these parameters. We initialize the logistic regression model with the best parameters obtained from the grid search CV. Next, we use this trained model to make predictions on the test data. To evaluate the performance of our logistic regression model, we calculate the accuracy score on the test set. The accuracy of our logistic regression model on the test set is 0.976, indicating a high level of predictive performance. Confusion matrix. We have the confusion matrix, which shows how well our model is performing by comparing the actual labels with the predicted labels. True positive, bottom right 130. Here, 130 cases were correctly predicted as presence of heart disease. True negative, top left 114. 114 cases were correctly identified as absence of heart disease. False positive, bottom left 2. only 2 cases were incorrectly identified as presence of heart disease when they were not. False negative, top right 4. There were 4 cases where the model failed to detect presence of heart disease when it was actually present. Classification report. On the right side, we have the classification report, which provides more detailed metrics. Precision. Precision for presence of heart disease is 0.97, and for absence of heart disease, it's 0.98. This means our model is highly precise in its predictions. Recall. Recall for presence of heart disease is 0.98, and for absence of heart disease, it's 0.97. This shows that our model is excellent at identifying actual positive cases. F1 score. The F1 score, which balances precision and recall, is 0.98 for presence of heart disease and 0.97 for absence of heart disease. Accuracy. Overall, our model has an accuracy of 0.98, meaning it correctly predicts 98% of the cases. So, the logistic regression model is performing exceptionally well, with high precision, recall, and accuracy, making it a reliable model for predicting heart disease. Let's move on to the support vector classifier, SVC, model. Now, let's optimize our support vector classifier, SVC, model by finding the best hyperparameters using grid search CV. We define a dictionary containing the parameters to test in the SVC algorithm. We instantiate the SVC model and apply grid search CV to find the best combination of parameters. After grid search CV completes, we print out the best hyperparameters found and the corresponding accuracy score. The best hyperparameters for our SVC model are C10, gamma, 0.1, achieving an accuracy score of approximately 0.963 on the training data. Moving forward with our support vector classifier, SVC, model, we use the best hyperparameters identified through grid search CV to train the model. After training, we evaluate the model's performance on the test set and obtain its accuracy score. The SVC model achieves an accuracy score of approximately 0.968 on the test data. Now, let's visualize the performance metrics of our support vector classifier, SVC, model using a confusion matrix and a classification report. The confusion matrix helps us understand the model's predictions, showing how well it classified instances into absence of heart disease and presence of heart disease. The classification report provides detailed metrics such as precision, recall, and F1 score for each class. Let's dive into these visualizations to gain insights into our SVC model's performance. Support vector classifier, SVC, performance. Confusion matrix. True positives, TP, 130 cases where the model correctly predicted the presence of heart disease. True negatives, TN, 112 cases where the model correctly predicted the absence of heart disease. False positives, FP, 6 cases where the model incorrectly predicted the presence of heart disease. False negatives, FN, 2 cases where the model incorrectly predicted the absence of heart disease. Classification report. Precision indicates how many of the predicted positive cases were actually positive. Absence of heart disease 0.98. Presence of heart disease 0.96. Recall indicates how many of the actual positive cases were correctly predicted. Absence of heart disease 0.95. Presence of heart disease 0.98. F1 score. The harmonic mean of precision and recall. Absence of heart disease 0.97. Presence of heart disease 0.97. Accuracy. The overall correctness of the model. 0.97. Let's move on to the decision tree classifier model. Now, let's explore the decision tree classifier and its tuned hyperparameters. We used a grid search to find the optimal settings. After tuning, the best parameters found were criterion, entropy, max_depth, 8, and splitter, random. This configuration achieved an accuracy of approximately 96.8%. Let's delve deeper into how this decision tree model performs with these optimized settings. Next, we apply the decision tree classifier using the tuned hyperparameters we discovered earlier. Here's how we fit the model and predict outcomes. The decision tree classifier achieved an accuracy score of approximately 95.6% on the test data. This metric gives us insight into how well the model generalizes to new, unseen data. Let's visualize the results with a confusion matrix and a detailed classification report to gain deeper insights into the model's predictive performance. Confusion matrix. True positives, TP, 127 cases where the model correctly predicted the presence of heart disease. True negatives, TN, 112 cases where the model correctly predicted the absence of heart disease. False positives, FP, 6 cases where the model incorrectly predicted the presence of heart disease. False negatives, FN, 5 cases where the model incorrectly predicted the absence of heart disease. Classification report. Precision indicates how many of the predicted positive cases were actually positive. Absence of heart disease 0.96. Presence of heart disease 0.95. Recall indicates how many of the actual positive cases were correctly predicted. Absence of heart disease 0.95. Presence of heart disease 0.96. F1 score. The harmonic mean of precision and recall. Absence of heart disease 0.95. Presence of heart disease 0.96. Accuracy. The overall correctness of the model. 0.96. Let's move on to the k-nearest neighbors model. Let's explore the k-nearest neighbors classifier using a grid search to find the optimal hyperparameters. We define a dictionary of parameters to test. Using these parameters, we perform a grid search with cross-validation, CV equals 10, to find the best combination. After fitting the model, we print out the tuned hyperparameters that yielded the best results. We also report the accuracy score of the model based on these parameters. The k-nearest neighbors classifier achieved an accuracy score of approximately 94.8% with the optimal configuration on our dataset. This score helps us understand how well the model performs in predicting heart disease based on the input features. Let's delve into the k-nearest neighbors classifier using the optimal hyperparameters found through grid search. Here's how it unfolds. We instantiate the k-nearest neighbors classifier with the best parameters obtained from the grid search. With the model trained, we proceed to make predictions on the test data. We calculate and round the accuracy score of the model on the test set. The k-nearest neighbors classifier achieves an accuracy score of approximately 96.0% with the best parameters identified through grid search. This score reflects the model's effectiveness in predicting heart disease based on the features in our dataset. Next, we'll visualize the performance metrics using a confusion matrix and a detailed classification report to gain deeper insights into how well the model performs across different classes. This function CLF_plot accepts the predicted labels y_pred_knn and generates two plots side by side. The left plot is a confusion matrix, which visualizes true positive, true negative, false positive, and false negative predictions. The right plot is a classification report heat map, providing precision, recall, F1 score, and support for each class. By executing CLF_plot, y_pred_knn, we gain comprehensive insights into the k-nearest neighbors classifier's performance on our test dataset. Now, let's take a look at the performance of our k-nearest neighbors model. Confusion matrix for KNN. True positive. Bottom right 127 cases were correctly predicted as presence of heart disease. True negative. Top left 113 cases were correctly identified as absence of heart disease. False positive. Bottom left 5. There were 5 false positives, where the model incorrectly identified presence of heart disease. False negative. Top right 5 cases were misclassified as absence of heart disease, when they actually had the disease. Classification report. Moving to the classification report, we can see the detailed metrics. Precision. Precision for both presence and absence of heart disease is 0.96. This indicates a high level of accuracy in the positive predictions. Recall. Recall is also 0.96 for both classes, showing that our model is equally good at identifying positive cases as it is negative cases. F1 score. The F1 score, balancing precision and recall, stands at 0.96 for both classes. Accuracy. Overall, the model achieves an accuracy of 0.96. Now, let's walk through the train and evaluate a Gaussian Naive Bayes model. Import and instantiate Gaussian Naive Bayes. First, we import the Gaussian NB classifier from the Exploratory Naive_Bayes module and create an instance of the model. Fit the model. Next, we train the Gaussian Naive Bayes model using the training data x_train and y_train. Predict with the model. After training, we use the model to make predictions on the test data x_test. Evaluate the model. To evaluate the model's performance, we calculate its accuracy score on the test data. We round the score to 3 decimal places for clarity. Print the score. Finally, we print the accuracy score of the Gaussian Naive Bayes model. We successfully trained and evaluated a Gaussian Naive Bayes model, achieving an accuracy score of 0.948. Next, we'll visualize the performance of this model using various plots and metrics. Now, let's take a look at the performance of our Gaussian Naive Bayes model. Let's dive into the details. Confusion matrix. First up, we have the confusion matrix. This matrix helps us understand how well our model is performing by comparing the actual labels with the predicted labels. True positive, bottom right 129. Here, 129 cases were correctly predicted as presence of heart disease. True negative, top left 108. 108 cases were correctly identified as absence of heart disease. False positive, bottom left 3. Only 3 cases were incorrectly identified as presence of heart disease when they were not. False negative, top right 10. There were 10 cases where the model failed to detect presence of heart disease when it was actually present. Classification report. On the right side, we have the classification report, which gives us more detailed metrics. Precision. Precision for presence of heart disease is 0.93, and for absence of heart disease, it's 0.97. This means our model is quite precise in its predictions. Recall for presence of heart disease is 0.98, and for absence of heart disease, it's 0.92. This indicates that our model is good at identifying actual positive cases. F1 score. The F1 score, which balances precision and recall, is 0.95 for presence of heart disease and 0.94 for absence of heart disease. Accuracy. Overall, our model has an accuracy of 0.95, meaning it correctly predicts 95% of the cases. So, the Gaussian Naive Bayes model is performing quite well, especially with a high recall and precision for detecting heart disease. Result. Let's walk through the compile and visualize the performance results of different machine learning algorithms. Create a results data frame. We create a data frame to store the scores of each algorithm. We include the algorithm names and their respective scores. Sort the results. Next, we sort the data frame based on the scores in descending order to easily identify the best performing algorithm. Set the color palette. We set the color palette for the bar plot to plasma for better visualization. Create the plot. We create a bar plot to visualize the scores of each algorithm. We set the figure size to ensure the plot is large enough for clear visualization. Add score labels. To make the plot more informative, we add labels to each bar showing the exact score of each algorithm. Rotate x-axis labels. To prevent overlapping of algorithm names on the x-axis, we rotate the labels. Display the plot. Finally, we display the bar plot to visualize the performance comparison of different algorithms. We'll look at a bar chart that shows the accuracy scores of each algorithm, making it easy to see which model performs best. Algorithms compared. The bar chart compares the accuracy scores of the following algorithms: Gaussian NB, a naive Bayes classifier; decision tree classifier, a decision tree algorithm; k-neighbors classifier, a k-nearest neighbors algorithm; SVC, a support vector classifier; logistic regression, a logistic regression model; random forest classifier, a random forest classifier. Accuracy scores. The height of each bar represents the accuracy score of the corresponding algorithm. Higher bars indicate better performance. Algorithm performance. Gaussian NB, accuracy score of 0.948. Decision tree classifier, accuracy score of 0.956. K-neighbors classifier, accuracy score of 0.960. SVC, accuracy score of 0.968. Logistic regression, accuracy score of 0.97. Random forest classifier, accuracy score of 0.980. Key insights. Random forest classifier has the highest accuracy score of 0.980, making it the best performing model among the ones compared. Logistic regression and SVC also perform very well with accuracy scores of 0.976 and 0.968, respectively. Gaussian NB has the lowest accuracy score of 0.948, but it still performs quite well. The bar chart clearly shows that the random forest classifier outperforms the other algorithms in terms of accuracy. This insight can help in selecting the best model for predicting heart disease. Final modeling. We proceed to finalize the model by fitting the random forest classifier to the entire dataset. Fit the model. Using the best parameters obtained from the grid search CV, we fit the random forest classifier to the entire dataset. Model summary. Finally, we print the summary of the finalized random forest classifier model to verify the parameters. We successfully identified the best performing algorithm and finalized the random forest classifier model for further use.
You can find all the code from my notebook using the link below.
We've gone through the entire process of analyzing cardiovascular health data, from data preprocessing to model evaluation. This analysis helps us understand the key factors influencing cardiovascular health and how we can use machine learning to predict health outcomes. Thank you for watching. If you found this video helpful, please like, share, subscribe, and click the bell icon for more content on machine learning and data science. See you in the next video.